So please accept Jeremy. Have fun.
Hello everyone, my name is Jeremy Levy. I'm going to present you the following presentation, Attack on Voice Conversion Models. So let's begin. First, I want to define some challenges that are specific to audio and speech analysis and not in the general field of time series. So in general, you have relatively long sequences. Speech is sampled at 16 kilohertz, which means 16,000 samples per second. So even if we have a few seconds of speech, we already have a lot of points. Second, we have relatively complex patterns, so a lot of information is encoded into this one-dimensional signal. We have information about the linguistic information, we have information about the speaker himself, his state of mind, and so on. Third, we have a lot of variability within the speech signals. We have variability across speakers, so different speakers may speak differently, but we also have variability within the same speaker. The same speaker speaks differently from one day to another, depending whether he is sick or stressed, and so on. And last but not least, a lot of factors have influence on the speech signal. We have the sensor, whether we are recording the signal with a microphone or with a high-quality microphone or with only a phone. We have the accent, the emotion, the stress, the speaker himself, and so on. Now that we have defined these challenges, let's define what is voice conversion and what do we want to attack here. So first, voice transformation is a field in which we want to change one or more aspects of a speech signal, but we want to preserve the linguistic information. The aspect can be the accent, the emotion, the speech rate, and so on. And then we have voice conversion, which is a subfield of voice transformation, in which we want to specifically change a source speaker speech in such a way that it will be sounded like a target speaker. Let's hear an example of the potential input of the voice conversion model.
But Buck was neither house dog nor kennel dog.
And this will be the output.
But Buck was neither house dog nor kennel dog.
So we can hear here that we hear the same sentence, the same words, but it sounds like a different person. A lot of efforts have been invested in the domain of voice conversion models in the past few years. Let's go very quickly over two examples of papers. So the first one I want to talk about was published in 2019 by Google. It is an autoencoder-based model that takes into input the male spectrogram, which is a spectrum normalized to the human ears. And the second one is a mass cycle GAN. It's a paper published in 2021 based on the architecture of generative adversarial network, or GAN. So we have a generator which creates the generative speech, and we have a discriminator which try to predict whether it's a fake or real speech. So my point here in this slide is that we have different architectures, different ideas, and to the best of my knowledge, we don't have a single state-of-the-art voice conversion model that is the best, and we want to be able to generalize our attack to different architectures. So let's define our goal here and what we are trying to do. So in the attack, we want to find out the identity of a speaker, even with a converted voice. So we have a speaker, let's call it speaker A, which will output a certain sentence. This will pass through a voice conversion model to be sound like a speaker B. And we want to ask ourselves the question, given these two recordings, is it the same person, yes or no? I want to highlight here that the two recordings that we'll be working on are not necessarily the same sentences or same words. It can be recording from different days, and then we'll suffer from all the variability factors that I've been talking about. It can be recordings with different sensors, and so on. Our main assumption here, our main hypothesis is that voice conversion models will leave an artifact. And this artifact, even if we can't hear it with the human ears, it can be exploited by the models to detect the identity of the speaker. So let's play a little game here, and we'll try to perform this task without a model. So let's hear two pairs of recordings. So this is the first one.
He was a merry monarch, especially so for an Asiatic.
And this is the second one.
Beyond refusing to sell us food, they left us to ourselves.
Okay, let's hear the second pair of recordings.
Please call Stella.
And the second.
Ask her to bring these things with her from the store.
So I think I have succeeded to convince you that it is not a trivial task. It's rather complicated to say at 100% whether these are the same person or not. And these are the answers. The first people were different speakers, whether the second one was the same person with the voice conversion models. Okay, so now that we have defined what we want to do, let's move to the, to the training itself. So we have based our model on a speaker verification task, which means we want to accept or reject the identity claim of a speaker. During a training, so we have a database of several recordings. Each one of them is passed through a backbone network, which will output an embedding, let's call it phi. This embedding will be processed by a classifier, which will output this one hot vector of length n, in order to perform the multi-class classification between the n speakers that we have in the train set. In this way, we can't generalize to unknown speaker, right? Because we are limited by the n speakers that we have seen, and we can only output one of these n speakers. For this reason, during the inference process, we'll not do the same, but rather we'll take as input two recordings, X1 and X2. These two recordings will pass through a backbone network in order to output two embeddings, phi1 and phi2 for X1 and X2. Between these two recordings, we compute the cosine similarity to get a continuous number based on which we'll perform the binary task to say whether yes or no, these are the same person. Okay, so in the first step, the SV model is trained on a large regular dataset, which means without voice conversion, for instance, or Vox Celeb. After that, we have created adversarial dataset using the voice conversion models. So we have an original dataset of several recordings, which will be passed through a voice conversion models in order to get D1. D1 is a replica of the original dataset, so it contains the same words and the same sentences, but with converted voice. We'll do that again for another voice conversion model, so we'll get different artifacts and different conversion of the voices, and we get again and again to get different replicas of the original datasets. Then we perform a fine-tuning of the SV model using the different replicas of the dataset. How we do that? We perform a classification of the converted voice, but obviously according to the original speaker and not to the converted speaker, in order to get a model which will be agnostic to voice conversion. Here in this work, we have tested two different attack scenarios. The first one will be the assumption of an unknown speaker. So we want to be able to generalize to unknown speaker. In order to do that, we have performed a split according to speakers, which means if we have, for example, three replicas of the same data sets, so the first two recordings will go to the train set, and the last same speaker will go to the test set. In that case, we don't have the same speaker which is present in two different sets. The second scenario that we have been looking is the assumption of unknown model, which means we put all of this model in the train set and all of the other one in the test set. In that case, we don't have a single artifact, a single model, which is in the train set and as well as in the test set. Okay, let's look at the metric to compare the different models. So we'll be using the equal error rate, or EER. If you look here at the DET curve, which is a false positive rate against the misdetection rate, we want to look at the location whether these two metrics are equal. So in the intersection with the y equal x axis. I want to highlight here that lower is better, and it is a binary task. So flipping a coin will get 50%. So if we have a result close to 50%, obviously we are not so happy, and we want as low as possible. Okay. If you are not be 100% with me, and now is the time to focus because I will summarize all of the attack before moving to the result. So we have, during the attacker training, we have a database of several recordings. We will use this database to train the speaker verification model. This same database will pass through different voice conversion models in order to get different replicas of this same database. The model voice conversion are pre-trained, of course. And then we'll use these different replicas in order to perform a fine-tuning of the speaker verification model. At this stage, at this point of the training, we have a pre-trained speaker verification model, which is agnostic to voice conversion, hopefully. Then during the attacker inference, we got two recordings. One of them is the original recording. The second one passed through a voice conversion model. Of course, we don't know which one, and we don't have the original recordings. We only have the two final recordings, which we will pass through our pre-trained speaker verification model in order to get the binary task, whether yes or no, these are the same person. Okay, let's move to the results. So in the first step, as I said, we have trained a speaker verification model on a large regular data set, which means without voice conversion. And we have tested it in the first step on a regular test set, which means without the voice conversion, only to get sure that our model converge. And we got an ER of 0.8%, which is the same as the state of the art today in the field of speaker verification. So we are happy. Then we have tested again an adversarial test set, which means with the different voice conversion, and we got an ER of 48%, which means a regular pre-trained model did not succeed to perform the attack, which is expected. But the interesting results are on the fine-tuning of the converted voice. So the first attack scenario was an unknown speaker, and in this case we got an ER of 2%. So when attacking new speakers, an unknown speaker, we did succeed to perform the attack. But an unknown model, we got an ER of 23%. It is not 2%, so it's not so low, but it's not close to 50. So we can say that the model did learn something. It did converge, but not to the same as unknown speaker. So we have decided to look a little bit closer at these results, and we have looked at, on this table you can see for each voice conversion model in the test set, so the three of the one for each row are in the train set. So we have the specific EAR. We can see that we have a relatively high standard deviation. Specifically for GAN models, we have relatively low EAR, whether for autoencoder models, we have relatively high EAR, so 38%. My interpretation of this is that even if these are two different models, for example, cycle GAN and star GAN, they are based on the same idea, on the same general architecture of GAN, and this helps the speaker verification model to attack. So let's move to the takeaways and conclusion. So from the point of view of VC models, I think that we have a need for stronger evaluation of the voice conversion models. For now, most of the paper only propose a human evaluation, but here we have proposed a scientifically well-defined metric to compare different voice conversion models. For the point of view of the attack, of the speaker verification attack, we have seen that diverse voice conversion methods can add robustness to the model. We have seen that voice conversion models, indeed, hopefully I convince you that they introduce an artifact in the generated speech. This artifact, we have seen how to use it in the case of the attack, but we can use it for any other task. And finally, using this VC model, for now, you may not be as safe as you think. Thank you.
Thank you very much. If we have questions from the audience, now is the time. Please raise your hand.
Okay, so first of all, thank you. Now, you said that it worked to some extent on models like CycleGAN, StarGAN. These are models that are trained without rephrasing the prosody. They work on the spectrogram. So basically, you're making a model that can rely on prosody to classify. even CycleGAN is prone to encryption, encrypting the information of the original speaker. That may be another way that your attack works, but what about the case where the prosody is rephrased? When a model rephrases the prosody, do you think the model will still have anything to work with?
If I understood right the question, you are asking about models that change the original content of the recording?
Yeah, voice conversion models today do a lot of working with the prosody, the rhythm of speech, not only the timbre.
Okay, you are right that there are a lot of efforts have been invested in disentanglement of the speech. For now, we have focused only on speech on voice conversion models that have been using the timbre and changing the timbre only. I think that in order to attack more developed model, which will change as well the speech rate and such a thing, it will be much more complicated. But it is an hypothesis. We can try to detect if there are some artifacts in these models.
Thank you.
Hey, I just wanted to clarify. In the first training phase, you're using the whole data set of the speaker, or you're leaving some out for the test?
We are leaving some out for the test, obviously. Because we are using the same data set for the voice conversion models, so in the assumption of unknown speaker, we are leaving out the same speakers for the pre-trained data set, for the pre-training, and as well as for the fine-tuning, in order to be consistent with the scenario.
So we have a little bit of more time. I have a question of my own. You discussed kind of a way to move from the cosine to, with the threshold to a binary decision. Can you explain how do you calculate this threshold?
Okay. So in order to define the ER metric is defined on a continuous number because it is the misdetection rate against the false positive rate. So we get this continuous number in order to define the metric. In practice, in order to use the model and to perform a decision, we have a need for this threshold. And we have been defining using a validation set. So we use a different data set, perform this same replicas, creating the same replicas, and then choosing the best threshold based on this validation set.
Thanks. And another question, if you can answer shortly.
Yeah.
You tried with unknown speakers or unknown models, right? Did you try to test against attacks, with both unknown speakers and unknown models?
So we did not try to both unknown speaker and unknown models. The reason that for unknown models it works not so good for now. We have a very high standard deviation. So I think that the most difficult factor to take into consideration is the model and not the speaker. So I think that it's best when focusing on the attack to focus on the voice conversion models. And the speaker we have seen in the unknown speakers that we got relatively low ER. So I don't think this is the main thing to take into consideration here.
Okay, thank you. And we have another question there.
Thank you very much for the presentation. The voice conversions models that are based on the generative adversarial networks, and as such they should be very easy to accommodate any new changes. So don't you think that, for example, they will be very easy to accommodate for all the remedies that you are developing, so they can develop faster than you can develop your models to identify their conversation, their conversion?
You are right that it is always easier to to build model for voice conversion than to build model against the voice conversion models. I don't think there's a reason to not do that in the first step, but I do think that no matter how developed you have the voice conversion models, it will always leave an artifact in the generated speech. And I think that this artifact will always be exploited. So it depends on how much effort and how much time you invest in it.
Thank you. I guess
Thank you very much.
that's it. Thank you, Jeremy. Thank you very much.